Hi, I'm Mike, and today I'll present our work on contention management with deterministic concurrency control. And this work builds on a lot of related works in deterministic databases and contention management, as discussed in the paper. But briefly, deterministic concurrency control is that given a predefined serial order for a batch of transactions, the database executes them concurrently while ensuring the outcome is still consistent with the predefined serial order. For example, let's say we have two transactions, T1 and T2. They are executed concurrently, but the database must ensure that their serial order is T1 before T2. In deterministic database, this serial order is established before T1 and T2 execute. And why deterministic concurrency control is so attractive? Because it avoids concurrency control related aborts. Transactions never have to abort due to concurrency. It's easy to scale out and handle distributed transactions. It also eliminates expensive two-phase commit because the serial order is predefined upfront. Deterministic concurrency control works really well for main memory databases because transactions are no longer delayed by long latency disk accesses. However, deterministic concurrency control suffers from contention and skew. In practice, not all the data in the database are updated evenly. Some data are much more frequently updated than others. For example, on Black Friday, some item became on sale. This causes bottleneck, slow down processing of other transactions. Another challenge is the skew. Data can be partitioned unequally across cores. So what happened is one core takes too long to finish the work, while other cores is idle. Both these challenges slow down the performance significantly. Now, existing deterministic databases often use two designs. So one design is called shared nothing design. The shared nothing design assigns the data partitions into cores, and it splits transactions into pieces. Each piece can only access one data partition, and that piece is scheduled to the assigned core. This design avoids contention, but skewed data access can cause load imbalance. Another design is shared memory design. So all transactions can access all data. Database can schedule transactions across cores. So this design can handle skew much more easily. However, in this design, cross-core data accesses can cause contention and thus slow down the performance. So our solution is to use a shared memory database to avoid skew, and then we can reduce contention by efficiently parallelizing and reordering data accesses. And we can do this because in deterministic database, serial order is known before transaction execution. Based on this, we propose two novel optimizations for reducing contention. We call them batch appends and split on demand. Batch appends handles contention during execution. Split on demand splits contented accesses and schedules them separately during execution. Here, let me show you how a basic deterministic concurrency control works. So we need to execute transactions concurrently while ensure the outcome is still consistent with the serial order. Now, this requires knowing the conflicts before transaction execution so that we can execute these non-conflicting operations concurrently. We do this by batching transactions. So transactions are executing batch by batch. Inside each batch, there are two phases, initialization and execution. In the initialization phase, we use transactions write set to convert the transaction serial order into row-level access order. So that in the execution phase, transactions are executed concurrently while simply ensuring the row-level access order. In our work, we use multi-versioning to establish row-level access order. For each transaction in the batch, we create pending versions for inserted row in the right set first. Now we do this because this allows us to determine the right set for range update operations. In this example here, T2 range update from R1 to R100. And then now T2 can simply do a scan in the database and it's going to find R1, let's skip R3 and R5. After this, we can create pending versions for all updated rows in the right set. After we finish initialization, we can execute transactions in the batches concurrently. For each write operation, it's very simple. We simply fill the pending version with the actual value. But for read operation, we need to be careful here. Here, we can see that T2 and T3 had a conflict with T1 because T2 and T3 needs to read T1's update. So the way we handle this is that when T2 and T3 execute concurrently, it's going to read version 1. And if version 1 is still pending, it waits until version 1 has a value here. So when version 1 has a value, it means transaction 1 has finished so that T2 and T3 can execute concurrently. T2 and T3 can execute concurrently because there's no conflicts between them. In a shared memory architecture, both these phases can be affected by contention. In the initialization phase, because we're appending versions concurrently, we may contend on the per row lock. However, we notice that in the initialization phase, appending version is a commutative operation. So our solution to this is to stash the append into a per core buffer. We only append to the row when the buffer is full or the end of the initialization phase. This optimization significantly reduces lock acquisition. In the execution phase, contention can also affect performance. Our observation is that only a small part of the transaction is actually contended. So our solution is to detect contended rows, split the access to contended rows and its dependent access into a separate piece. And then we schedule these contended pieces separately and run them on fewer cores to reduce contention. And of course, this scheduling must be done in a way that's load balanced so that we don't have any load imbalance on the CPU. So how should the pieces be scheduled? What we want is to cluster pieces for each row on fewer cores to reduce contention, while at the same time providing load balance. To avoid contention when dispatching pieces, our solution is that each core independently dispatches a set of pieces using probabilistic assignment. So here's an example. Suppose there are 3 contended rows, and altogether we have n total number of pieces. What we want is evenly distribute these n pieces to 4 cores. This is how we keep load balanced. So on each core during dispatching, let's take row 2 as an example. We first generate a random number between n1 to n1 plus n2. Now, depending on where this random number lands, we're going to dispatch this piece to either core 2 or core 3. So this is how we guarantee load balance while clustering these pieces. So we evaluate our approach with all partition-based system. In this workload is YCSB low contention workload. Even with uniform access pattern, we can see that our approach performs significantly better than partitioning-based system. This is because partition-based system had a cost of splitting, while shared memory system does not need to split. As we add more skew into the workload, we can see that we our performance stays constant, while the rest of the partitioning-based system drops significantly. This is because they all suffer from load imbalance. When we add more contention to the YCSB workload, we can see the partitioning-based system performs significantly better. In fact, this is the best case for partitioning because it can avoid contention efficiently. However, for our approach, we can also see that we're catching up pretty close, even though we're shared memory. Again, as we add more skew into the workload, a partitioning-based system suffer from load imbalance. Well, we can see our approach still scales. We also evaluated our approach on TPCC benchmark. With the default TPCC is uncontended, it's also very cache sensitive. So as you can see, all single version system perform significantly better than multi-versioning system. Our approach performed very similar to BOM, which is another multi-versioning system. As we add more contention and skew in TPCC, we can see all of the partitioning-based systems suffer from load imbalance, but our approach still scales linearly. In summary, we propose our solution, a shared memory deterministic database that avoids partitioning data. Our design is high performance and skew tolerant. We propose two novel techniques for handling contention: batch append, which reduces locking overhead during initialization, and split on demand, splits and schedules the content pieces to reduce cross-processor traffic.